Uh, Azadeh and Mahmood have already talked about uh, what the databases are and what use they have in the archaeology. So in this session, we will be looking at into what are the spatial databases and how these are different from conventional databases. You will be seeing this laser pointer that is currently below the introduction word that I will use to navigate around the content present on the slides. So the agenda items for this session are what is spatial data, the associated concept of geometry for spatial data, and uh, and also we will see where the spatial databases fit in the context, the associated spatial data integrity and constraints, how we can answer spatial queries with example of some spatial operations and how spatial databases are optimized for this. And finally, we will look into some of the application areas that is covered by spatial databases. Okay, so to begin with, what is spatial data? Uh, Spatial data is any data that can be displayed, manipulated, and analyzed by means of the associated spatial attribute that denotes a location, which tells us where our feature or data is present on the surface of the Earth. Uh, so, so if we see uh, that do we use spatial data in archaeology? The answer is yes. We use spatial data in archaeology because a lot of data that we are dealing with contains the information that where our site is located on the surface of the earth, and it is usually present in form of in a form of coordinates, xy values that are xy values which we saw in the database example in the last session where Mahmood showed us the table. So an important question that rises at this position is that at this point is that because Earth's surface is quite large and the data is being developed in different countries and different regions across the globe. So is there any system present that allows us to uniquely identify these locations over the surface of the Earth and make sure that when this data is going to come together from different sources, it falls on the correct location on the Earth's surface and is in correct position relative to each other. So there are systems for that, and these systems are known as geographic coordinate systems uh, that allows us to uniquely identify our location on the surface of the Earth through a use of coordinate values, that are basically x and y values, so that when the data from different sources is combined together, it can be cross-referenced and also integrated spatially. Uh, let's look into a sample and let's look into an example of the spatial data. So here we have uh, two boundaries. One boundary is for the Ireland and another boundary is of United Kingdom. Now we want to make sure that our boundaries are falling on their correct location on the surface of the Earth and also in correct locations relative to each other. So when both of these boundaries are registered to same coordinate system, uh, and these are merged together, we can see that these are falling on the correct that these are falling on the correct location and also incorrect relative location to each other on the surface of the earth, right? Uh, so now let's look into how we can store our data in form of these boundaries and what is the uh, associated concept for this. So now we will be looking into the concept of geometry of spatial data. Uh, Commonly, uh, we might be familiar with the geometry as the branch of mathematics that deals with different shapes and the relationship between them. In the context of spatial data, geometry is used to represent the spatial component of a geographic feature, that is its location, its shape, and the geographic features can be wells, mounds, streets, river, land parcels, or any other data set. And we will be looking into some of the examples of these features as we progress along with the presentation. So geometry can be represented as a simple point. It can be represented as a line or a polygon, and there are other more complex shapes that can be used to represent the geometries. So starting with the very basic type of geometries, that are basically point geometries. So point geometries are individual X and Y locations. Uh, we can represent different data using point geometries. So this is one location, this is another location, this is the third location. So the type of data set that we can represent using point geometries could be simply a tree. It could be the center point of an archaeological site, or it could be a center point of a plot location. Can we think of any other examples that can be stored as point geometries? So yes, we can possibly represent and store our electricity poles as point geometries. We can store the location of bus stops as point geometries. And there can be other examples as well, depending upon the data that we are using. So these individual X and Y locations can be seen as the building blocks for more complex geometries, because we always need these pairs of X and Y coordinates so that we can move towards more complex geometries that we will seeing here. So the next type of geometry is a line geometry. Line geometries are composed of, these can be composed of many, but at least 2 points. These points can also be referred to as vertices here, that are connected with each other. So we need at least one and at least 2 points that are connected with each other to form a line geometry. And then we can possibly extend our line geometry with including of more points or vertices, so that our line geometries represent the data that we are trying to do so, trying to represent. And the examples of line geometries include, we can represent a river as a line geometry. We can also represent a road or a highway as line geometry. For example, in context of archaeological data, we can, if there is any dirt track or any road leading to our archaeological site, that can be stored as a line geometry in our data set as well. So now let's look into the next type of geometry that is the polygon geometries. So polygon geometries need at least 3 vertices present in the geometries that are connected with each other and are also closed, so that uh, it gives us an indication of the extent of the area and extent of the boundaries of the data that we are recording. So this is one vertex, this is second vertex, and this is third vertex, and these are connected with each other in a way that these are closed, that these form a closed shape. Uh, so what can we store? What data can we store as polygon geometries? We can store archaeological site boundaries as polygon geometries. We can have building geometries as polygon geometries. We can have park boundaries as polygon geometries. So, and there could be many other examples to be stored as polygon geometries. So let's now see where these geometries fall in the context of spatial databases, uh, and why these are usable. So Mahmood has already shown in his presentation that the data types we use in our databases to store the data values and attributes allows us to interact with that data in a specific way. It gives us it allows us to perform certain operations and certain processing depending on the data type. For example, if our data is stored as a character string, it would allow us to perform certain operations associated with the string types. If our data is stored as a numerical value, then there would be numerical operations available. If we have stored it as a date or another data type, and then the operations that our database system would allow us for that particular attribute would be very defined and restricted to that particular data type. So conventionally, the database systems were designed to manage and process alphanumeric data represented by character strings, numerical values, dates, and there was no provision in a conventional database system to support the storage and processing of geometries as special data types. So let's support it with an example over here. This is our data table that we need to record in our database. Here are different attributes. each having in its own data type. And here we can see we have the location information present. So we can possibly store this location information as a string or as a numerical value. So just assume that if this location information is stored as a numerical value, what value does it generate for us? Because on a numerical value, we can certainly perform an operation like addition or subtraction, but this is not very helpful and not allowing us to make the most of this information available within our database. So we need our database system. So we need our database system to understand that this is a special type. This is a special type of data, so that we can generate maximum value from this information. That is storing it as geometries within our database system. So this is where the spatial databases come in. How we can assign it a spatial data type. So let's now look into the what are spatial databases. I mean, we have seen this from the last slide. It is a special type of database system that is enabled to manage and process spatial data. We can store our data. We can store our data in the database system using special data types. So the characteristics of a spatial database system are as follows. It is simply a database system, so that it provides the functionalities that have been discussed by Mahmood in the last presentation. However, it is extended so that it offers spatial data types in its data model, and it also allows us to support the and it also provides us the query language that we need to answer some of the spatial queries related to our spatial data types, and provides us with an efficient mechanism known as spatial indexing that allows us to quickly retrieve these results. Let's look into more examples. So our spatial databases are now able to handle and relate spatial and non-spatial data simultaneously. When we look into a conventional database system, this geometry information was available only as a readable text or a numerical value, but now that it's stored within our spatial database as a geometry. We can display it on a map. We can see where it falls on the Earth's surface, and all of the non-spatial attributes are also binded and related to this location now. So when we can click on this on the geometry and see what all of the non-spatial information that is related to this geometry. For example, this is the site X. It has site feature is lower town from Iron Age, and multi-feature and shape is irregular, or and so. And this geometry in a human readable way, this geometry looks something like this. It tells us that this is a point geometry. It has an X value and a Y value that is allowing us to deal this in a spatial way. Now we have our data can be present in the different geometries depending upon the information that is available with us. So for example, if there is a site X and this is a large mound and we have a polygon geometry available for it, our geometry tells us that this is polygon, and here is a sequence of XY values available here. When we display it over satellite imagery, it is available as this large round red boundary that is indicative of extent of this mound. And we have only point information available for our lower town feature type. So this can be seen here as a point geometry with an X and Y value, and this is plotted on the satellite image using this green point here. So when we are dealing with our spatial data in the spatial databases, and we need to be certain about the quality of the data that we are dealing with, so that our applications and the database is uniform and is of the best quality that we can achieve. And for that, we have some data integrity constraints. that we can implement on our data set so that our data is of the best quality, and eventually the services and applications that are provided on top of it are also accurate and error free. So first of all, we will be looking into this topological integrity constraints. These are the constraints which are concerned with spatial relationship between the features, uh, that how they relate with each other in terms of their location, and this is built upon three main principles of adjacency, how these adjacent features relate to each other, connectivity, if these features are connected to each other, uh, or about the containment, whether our polygons are contained within other polygons. So let's try to understand this with the help of this example. Consider these two boundaries as the boundaries of our archaeological sites. So we can have a rule for our data set that these our archaeological site boundaries are not allowed to overlap with each other, and neither the adjacent site boundaries uh, can have a gap between them. So we can now quickly identify uh, any data that has errors, such errors in between them, and we can clean it up so that our site boundaries follow our rules, our defined rules, and are very clean in terms of data development. And these topological constraints vary according to the geometry of the data that we are using. For example, for line data, there could be a constraint that our line geometry should always be connected with each other. In terms of a point data set, we can implement a constraint that there should be no same geometries and no two same geometries in our data set, so that there is no duplicate data. Uh, and some of the other types of constraints that we can implement on our spatial data include the semantic integrity constraints, which are basically the database rules that govern the spatial behavior of records in the database and are mainly related to the meaning of the data that we are dealing with. For example, if we are dealing with a real estate or a parcel database, uh, we can have a semantic integrity rule that no land parcel can be located in areas shown as water bodies. Again, this is very subjective to the type of the data that we are using and relates to the meaning of the data. And also, we can have a user-defined constraints that deal with the spatial aspect and the locational aspect of the data so that our application works fine. And an example of this could be that no construction is allowed in 500-meter buffer zone of a heritage site. So if there is a 500-meter zone, a polygon boundary of 500-meter around an heritage site, no new construction or new construction building is allowed within the geometry. This is also dependent on the our application and hand and the type of data that we are dealing with. Okay, so now we saw that we have our database stored as our locational data stored as spatial types in our database. Our databases now allow us to answer the spatial queries that would not have been able to be answered by a conventional database system. So can we think of any spatial queries that we might come across in our archaeological data set? Here are the example of some spatial queries. We might need to find all archaeological sites that are intersected by a water body, for example, a canal, or this could be a river. Uh, or we may need to find all the site features, for example, bounds that are contained in a larger site boundary. Or we might need to find all the archaeological sites within 50 kilometers of Cambridge city center. So these are just some examples of a large spatial operation that are allowed by our spatial databases. Now let's see which type of spatial operations can allow us to answer these spatial queries. So starting with this, finding all archaeological sites that are intersected by a water body, we have a spatial operation available for that. That is st intersect. and it returns true if the two shapes have any space in common. Uh, so basic, if we have our data set stored as a point geometry, two data sets of point geometries, we can check if they intersect with each other. Similarly, we can do this operation for a line and a line geometry, or a polygon and polygon geometry. This could be done for different types of geometries like point and line geometries, uh, or a line and a polygon geometry, or also for a point and polygon geometry. So if we say if we revisit our query that we need to find all archaeological sites that are intersected by a water body, and say that our archaeological sites are stored as the polygon geometries, and the line geometries are stored, and the canal or the river feature is stored as a line geometry. So our scenario would fall in this particular category of ST intersects, and our databases would be allow us would provide us with the results of the subset of the data that tells us and that gives us the all the archaeological sites that are basically intersected by a water body. So for our second case, where we say find all the site features, for example, mounts that are contained in the larger site boundary, we have a spatial operation known as ST within and ST contains that tests whether one geometry is fully within the other geometry. So again, we can handle multiple geometries with the spatial operations. Here you can see the operation for point and point geometries, or line and line geometries. You can see there is a white line over this dark green line, or there could be two polygons, as this is a black polygon or this is a green polygon. Similarly, for point and line, we can perform the operation for line and line polygons, and point and polygon geometry types. So for example, if our if our mounds are stored as point features, and the larger site boundary is stored as a polygon geometry, we can use this, and we will be using this scenario to find all of the mounds that are contained within the larger archaeological boundary. And our ST contains function would return true when we will say give us all the mounts uh, that are uh, that are contained within the polygon geometries or within the this polygon geometry. Let's look into another type of spatial operation available. This spatial operation is useful for questions like finding all the archaeological sites that are within a 50-kilometer buffer of the Cambridge city center. And our database systems allows us this privilege that we don't have to calculate and save an actual buffer area. You just have to test the distance relationship. For example, uh, in a normal system, when we have to compute this 50-kilometer boundary around the Cambridge city center, we will have to store this intermediary result as a separate file that could be used in our spatial operation. But with the help of this spatial operation, that is STD within, we can simply get the results of our query in a one step. So our database system would now return us all the archaeological sites that are within the 50-kilometer buffer of the Cambridge city center. So for example, this is a Cambridge city center, this is a 50-kilometer buffer, and these are the archaeological sites that are finding that are falling within that boundary. This function would be returning true for that. Okay. So let's see how our database systems are optimized for these types of spatial queries. Because we understand our database can store a large number of records, and we might have time performance issues, as were shared highlighted in the earlier presentation by Mahmood, uh, and how our database systems can support us to speed up these queries. So our database systems provide us with indexes, which are very powerful tools that are used in background of a database to speed up the query process. They allow us to quickly locate the data without having to search every row in a database table every time a database table is accessed. So we can see that the indexes within a database are very similar to the index at the back of a book, which allows us to quickly navigate our way because it provides a sorted structure for our words that are available in the book, and it tells us about the page number where we can find those words. So our database system use a similar sort of way to quickly retrieve the records, and within a spatial database, this is extended as spatial indexes that allow us to quicker execution of spatial queries. Uh, there is a complete mechanism on how the spatial indexes are implemented and how this allows a quicker execution, uh, but this is more complex, and for this session we will not be going into the details of these spatial indexes. Right. So, uh, so when can we choose a spatial database? If we can quickly summarize what we have learned so far. So whenever we have a spatial database, whenever we have a spatial data set that has some location information, and we want to store uh, our location information in specific spatial data types, that are the geometries, and we also want to implement some of the integrity constraints on our data set, and we need to perform some spatial operations so that we can answer spatial queries, like we have seen in terms of the locational context. Then we can and we also need our database system to provide us with the efficient execution of these operations. Then we can choose the spatial databases. And here are some of the application areas that deal with the spatial databases. So there are archaeological heritage inventories, something that we are trying to deal with because we have a lot of site records that have spatial attribute and location included in it. Uh, there can be land title registrations. These types of systems would include the polygon boundaries of different plots and different. These could be agricultural fields, so that we can know what is the extent and the location of these plots and fields, and use it as a part of land title registration systems. We can use these spatial databases for forestry resource inventories. For example, there can be a lot of data set of point geometries that tells us the location of the trees. There could be boundaries of forest that tells us the jurisdiction of that tells us the reserved land boundaries of the forest, and could also be indicative of the jurisdiction of the forestry department. So we can use spatial databases to handle that type of data. In case of census and population and housing, we know that our census is divided into different blocks that are divisions of towns and cities, so that we can aggregate our population information according to those boundaries. So in this type of application, we can have these large town blocks and census blocks available as polygons, and the housing information can be stored as point geometries uh, to deal with and provide services for this application. Similarly, we can also use spatial databases as inventories of highways. This would include the line geometries for our roads, uh, highways, any. We can include other data sets like railway tracks as lines, uh, or any routes. And in terms of the public infrastructure, such as water mains, electricity, and the gas distribution systems, we have already seen that we can potentially represent the electricity poles, uh, as point geometries. These gas meters and these gas recording meters can also be represented as point geometries, their locations. And the water mains, these could be the water main pipelines, which could be stored as the line geometries in our database. So this is pretty much it with the spatial database applications. We have if we can summarize what we have learned in this session, we now know that location is very important in any data set, and we need to store it as a spatial data type so that we can use our database system to interact with that with our location in a specific way, and our database system can help us to answer some of the locational questions that we have about our data set, and this is also in an efficient and optimized way. Uh, and while we are developing the data, we can apply some of the integrity constraints on our data set. So this is pretty much it. I realize I have finished before my time, but if you have any questions, I'm happy.
Yeah, it's just when we're making databases from maps, and we have many maps dating back to the late 19th century, some of them, they use a whole variety of different types of coordination systems, and which vary and can be from different, they can be different coordinates. German systems are different from British systems, from French systems, from systems developed in different regions of the world. And I was wondering, is there any system within your experience of databases where you can enter these different coordinates and you can actually link them together to form a coherent system or to the main system?
Yes, that is a really great question. And so I assume you are using some old maps, possibly you're referencing these maps and identifying the sites from these maps. But in the start of the presentation, where I explained that we have these geographic coordinate systems, so there is not one coordinate system, but there are many coordinate systems that fit in different regions of the world to increase the location accuracy that they provide to us. So when you talk about that, there are different systems. Some are French systems or some are other systems. So on top of this system, there are other coordinate systems as well that allow us to approximate and uniquely identify these locations with high accuracy over the whole globe. So our database, as we, as I just presented you some of the spatial operations. Yes, so databases also provide us with the spatial operation that is referred to as ST transform. And what this operation allows us to do is that we can define that our original data set has our coordinates available in maybe a French coordinate system. And we want to transform these coordinate values into a global coordinate system. So yes, we can certainly do that within the databases. If that answers your question.
Yeah, thank you very much. Very good. Thank you.
Measure the size of archaeological site.
Sorry?
How to measure the size of archaeological sites?
Okay.
You mentioned so, site is large, site is small. How to measure?
Yes. I mean, so I can see this question with the respect of with two perspectives. First could be what methodologies maybe you can use within the field to record these types of site extent. But I will not go into that detail. I can tell you how we can store this size within our database. So as we looked into different type of geometries like point geometry, line geometry, and a polygon geometry. So the point geometries don't give us any information about the extent or the size of the site. These only give us the information about the unique XY location, that this is a site present here at the surface of the earth, but these are not giving us any information about what is the actual extent of the site. So one way is to store our archaeological sites as polygon geometries so that we can see their extent on the map when this is plotted, or otherwise, and then to to actually know what size our archaeological site is covering. For example, it covers maybe 5 acres, 5 hectares, or any other unit of measurement. We can have a separate attribute value for that in our database. So that links us with us. That links to our record and the geometry, and it can tell us the numerical value for the area of the site, that it is a 50 hectare site, 50-acre site, or any other unit of measurement. Uh, does this answer your question? Sorry, you are on mute.
Can I suggest a very small thing?
Yep.
I think we should try to use alpha line twist and try to take a perpendicular transects and for the measurement of the site, and also for the knowing of the cultural material on the site, I think. And then I think you should try to read Adam Green paper published in 19 in remote sensing. Also Hector Ringo, Cameron Petrie, Lily Green, many authors is working, and I worked together. And so we tried for the uh, for this method in Haryana. So I think it's very good for measurement and also the for the cultural material.
Yes, you are very right about that. I mean, this transact method for identifying the site measurements is very good method, and this is something that we will be addressing at the data collection phase of our project, where you have talked earlier about the ODK forms. So we can potentially have separate forms that allows us to record these transacts measurements, something that you are referring to in respect of the Adam Green's paper that you have mentioned. Uh, but that is something at the data collection part, and it is really important phase of the project. We are devising methodology around it. However, databases come at the point where we have to store and manage the data set. So yeah, collecting that is another stage. We will be hopefully be in contact with all of the collaborators and devise a strategy around it. And then after the data is collected, it would be stored in the databases for which we are using the Arches platform.
Could I just also add to that, and thank you again to Aftab for raising the point. Yes, so the MAHSA project is building very much on the Two Rains project and methodology. So Cameron is taking, his previous experience, and we're working closely with everybody on Two Rains and to use this tried and tested methodology, particularly with regard to site extent. So thank you for making that link clear. And yes, it's certainly part of our methodology. So thank you.
Thank you.
Thanks, Aftab. And the next person I have is Jidere. Yes, if you can unmute yourself and ask your question. Thank you.
Thank you. Good morning, everybody. I'm Jidere Balde from Senegal. My question is if it's possible to use this system to draw the artifact or the monument, like the megalithic.
Okay.
You understand me?
Yeah, so from what I've understood, you are asking if we can use this system to draw the artifact.
Yeah.
Yep.
Or monument like the megalithic.
Yes, I mean, yes, thank you. That is a good question. So in terms of this system, we can take the concept of drawing as making the geometries of our features. So for example, this system would definitely allow us to draw a polygon geometry of our feature like you are referring to, or possibly allocated a point geometries. But it cannot allow us to go into a lot of structural details in terms of drawing. If you are looking for that, there are other systems for that allow us to make architectural components and drawings for that. However, we can most certainly draw the geometries and boundaries for our features that we have to record.
Right. Thank you.
To add on that, Judera, we will explain this more on Arch's part, but you cannot use this specific database itself for drawing. As Junaid said, there are other softwares, but you can do is to store the PDFs or the images of your drawings in connection with your sites or your monuments. So you can, after producing, you can use it as a repository to add those elements to your sites. And you're welcome. Thank you for your question. And the next person I have here is Kazala. I hope I pronounced your name correctly. I'm sorry if I'm not.
Thank you. You pronounced it very well.
I'm happy.
Yeah. Okay. For me, my question is very general. And first of all, I'm a student studying in Italy. I'm basically Zambian studying on Southern African settlements. And my question is a general one. I think I'll throw it to everyone. Or yeah. Well, I'm dealing with spatial recognition for satellite imagery. And what I'm trying to propose is to use, for example, machine learning or deep learning, any AI-related technique as regards to recognition of new archaeological sites based on training the existing sites. For example, let me give you a practical example of the UK itself. For example, if you are studying stone settlements, for example, stone walls and all that. Now, once you put all that data in the computer, if you're using deep learning techniques or machine learning techniques, it gives you results from the images recognized through the neural networks and all that. But my question is, have you tried to do any or to create any database based on the results of any machine learning outcome? For example, if you are dealing with the site in question, I gave in an example. If you get certain results, how are you able to put those results in a database? For example, if you discover a new site in the UK, how can you put those coordinates? I'm sure maybe it might be easy using georeferencing and all that, but you don't know exactly where the site is. So it's more like finding a needle in a haystack. So how do you manage such kind of data to by creating a database for others to work on it? I think that would be my question. I don't know how clear it is.
Yeah, I mean, that is a really good question, and I'm happy to answer and see if anyone has to add anything to it. So the thing that you have directed us towards this machine learning and spatial recognition using the satellite imageries and other data set, possibly historical maps, is a very good way of bulk identifying these locations, because these large data sets like satellite imagery or historical maps are they cover a large spatial extent and large region of the world, and we can also get this data set from older days that allows us to see whether a site was present at a particular time or not. So when we talk about how we can get this information from these sources and store it in a database, so this is a very detailed multi-step process. So it starts, I would say it's, so the input that we are giving to our machine learning algorithm, so it is supposed to contain, if we want to get an output of locations from this algorithm, then we have to feed the data that we are feeding to the machine learning algorithm. It should include some spatial information with it. So if you see these satellite imageries, they already registered to a coordinate system. In terms of a historical map, if this historical map is a flat file, then you have to georeference this historical map so that it includes some of the spatial information. And now when we feed these input data sets to our machine learning algorithm, they generate an output value, and this could be, this could be dependent on the algorithm that what output it generates. So for example, one example could be that algorithms tells us the boundaries or of the mounts. For example, our satellite has a lot of mounts present on it, and then our machine learning algorithm can give us the polygon geometries uh, from as an output. Now we have this bulk of polygon geometries available. We can upload these geometries in the geometry attribute of our database. And if there is if there is any other attribute that our machine learning algorithm generates, maybe for example, if it is very sophisticated to give us a measurement of the area, or maybe the color, or maybe any other information for that particular feature, then all of these values would go into separate attributes within our database, so that our machine and database systems are able to intelligently interact with these, and we can perform our required analysis or anything like that. So yeah, we are certainly looking to use some of these methods to speed up the process and get good results.
Thank you very much. That's a very wonderful answer.
Yeah, no problem. Yeah, there is a.
I think it's a comment about connection.
There is a question from Sabah.
Oh yes, sorry. Yes, Sabah, go ahead. I'm sorry.
I don't know how relevant this question is, but so we're talking about spatial location of the sites, archaeological sites. Can we also do temporal analysis using arches and these softwares? Can we do like temporal analysis as well?
So I will maybe Mahmood, you can add up to this, but for in terms of if you consider this time structure in because temporal is essentially related to time. So if you are referring to any temporal analysis in terms of change detection or comparing different data sets, then you can possibly not do this within arches. You will have to use another external GIS system that allows us, and remote sensing software that allows us to compare multiple images and get the results. However, arches do allow us to filter our records based on the time period associated with these. So we will be seeing in the next slides how we can structure our data within the arches, and we can associate different cultural periods or different timestamps with our data set. And then arches would allow us to query our results within the database based on the associated time periods that are available within the data set. Mahmood, is there anything you would like to add?
Yeah, sure. I'm going to reiterate the bit that Arch is not necessarily the most powerful tool in terms of processing temporal data, as in time series data, if you're looking into something similar to this. But yes, the underlying structure of arches, so the technologies used within arches has the same tools. It's just not available through the interface because this is not the target. And adding this to the interface will just make it convoluted. So you have to aim towards a specific use case, and this is what Arches is serving. But the same tools as Postgres, Elasticsearch, GDAL, if these tools are relevant, you can use them to do the same type of analysis that you're looking for. I might add that specifically in terms of time series, if you can extract the signal, so if you can extract what you're looking for instead of having to do the analysis on the image directly, then there are specific types of search engines and database engines that you can use just for this particular type of analysis. But not, I wouldn't say that this is the main use of arches.
Okay, yeah, thank you.
Okay, thanks for all the questions.